Okay. Before I get to this, let me just come back to where we were. Okay, so last time we got started with unsupervised deep learning, and we wanted to discuss variational encoders, and we just started talking about what are autoencoders. Okay, so that's the context from last time. And where are we? We are, I guess, 36, right? Oh, okay, so we are here, and there is actually going to be quite a few weeks where there's a lot of other things happening. But in particular, next couple of weeks, so 13th and 27th, there are meetings for making improvements on your project. And in between, we also have a spring break. So try not to kind of lose momentum while working on projects for this. But hopefully these two checkpoints are really for ensuring that you are actually making progress over those 1-2 weeks period. So what I want to do is actually, before get into today's content, which I just mentioned is about VAEs and so on, and GANs as well today, I want to briefly discuss about the projects. So for the next 15 minutes or so, just more information of the project so that if you have not yet decided, or if you have also decided, that's fine. You can start thinking about some really exemplar projects and getting a sense of, okay, what do you want to do? Okay. So first, example. So let me give you an example of a project. Let me go to my courses and okay. So I have added an illustrative project link on Blackboard. Started going to assignments, but added it to the location here. But basically, it's just a slide deck from one of the projects from before. Okay. So yeah, just wanted to show you this is an example project of what you can do. So I'll just walk through it. We haven't discussed the techniques used in there because it's about reinforcement learning, which we're going to talk about in the remaining lectures, in the lectures perhaps after the spring break. But this was a project done by a group which involved PhD students, but it's still in the same course. It's a course project, but the student extended. So the slide decks may look more polished because students worked a little bit more on it. So what is the project about, right? So this project was not so much the details. This project is about picking up a model. So just like we have been mostly looking at supervised learning, and today we'll look at unsupervised learning, but picking up a model and a canonical model that we have seen in the class, and then look at a couple of papers which kind of slightly change the model. Like it's the same model, but maybe an extra attention head or something like that. Okay. So, and then really bring an application that the student was involved in. Mostly it's a transportation related application. It says crowdsourcing here. So the student is a domain expert, or at least has experience in transportation and what is crowd shipping and things like that. And so he wanted to use, yeah, so they wanted to use the reinforcement learning approach to kind of figure out how to crowd ship. Okay, so that's the problem, and the title is quite long. It says it actually tells the solution of how they did it, but the group basically brought a problem called crowd shipping problem, defined it appropriately, and then all the project effort was just to define the appropriate inputs and outputs for this model. So the model is not, there's no innovation, obviously. I mean, it's okay. You define, like just like ResNet 18 that you use in assignment, you can always start with a canonical model or just use the pre-trained model. So you don't have to innovate on like, okay, let's fine tune and improve some numbers. That's not, you can do it, but I think that's not very useful, and that may even need a lot of resources. Okay, so but here is an interesting application where it turns out the network is not big in this project, but the group basically matched an applied problem to the model at hand and kind of made some progress. So what is crowd shipping in this project's case? Crowd shipping is just picking up of requests, parcel pickups, and delivering it to appropriate locations. And this is done by some people. Okay, so now what's the difference between people and vehicles? Actually, for the computational problem, it's really there's no difference from the computational perspective, but in the motivation perspective, they're talking about crowd shipping here and why it's interesting. But what is the problem, right? So the problem is people or vehicles, are in the system that they're imagining, and there are requests that are also there in the system that they're imagining, and so a computer or a computational system needs to just match these requests to the people, which are called crowdsources. Okay, just matching. So that's the computational problem. So how would you match? There are many ways to kind of say, oh, this request should be picked up by this crowdsourcer at this time, and and things like that. And the interesting thing is you may want multiple requests if they're on the same like path. Then maybe the crowdsourcer can pick up request one parcel, pick up request two parcel, and then drop off appropriately. So there is some this is called a combinatorial type of a problem, in the sense that there's many ways to kind of match crowdsources to requests. So it's generally a hard optimization problem. If you've done some optimization or operations related type of topics, then this is a kind of a hard thing. You can always have some rules of thumb, policies, ways to kind of figure this out. And so since the team was a domain expert, kind of domain expertise in this, and so they knew what is the objective. Okay, they want to minimize shipping cost of shipping these parcels, and they kind of knew how to kind of say what the optimization problem is. It's just that they wanted to use ML to kind of solve that optimization problem. That's new, and that's also not something that they invented or anything. There has been history of using defining an appropriate optimization problem, in this case matching type of a problem, and mapping it back to some machine learning tool like an LSTM based sequence approach, sequence modeling approach. You may say, how is it related, right? So many of these machine learning tools, what they do is, it could be LSTM, it could be some reinforcement learning approach here. They all try to incrementally match. So given the current solution, it's like a variable length input. You want to say, okay, what is the, how do I fix, or how do I make the solution slightly better? Okay, so some sort of a one step at a time kind of defining the solution of who gets matched to what. Okay? So that's the approach in these types of problems, combinatorial problems. And so the team's effort was mostly, all I'm saying, is on the domain side. And once they define, so it turns out in this problem, the key thing is to do assignments. And how do you do the assignment? They picked deep reinforcement learning as a tool. There's another team which also used deep reinforcement learning for a traffic related problem just last semester. So giving a sense of like, this is not something we've covered, so it might look a little bit alien. They use a tool, I guess, framework of deep reinforcement learning, or a category of problems and solutions in that subdomain. And what they did is kind of go beyond the canonical model, and kind of appropriately define what is called what actions to take. Like, as I said, incrementally you want to define the solution. How does the ML model incrementally kind of define that, how to match? Because they had domain expertise, they defined something different. And there are also hard constraints, because pickups, like if you're delivering a takeout, like some food, there is a time limit, right? 2 hours or something. So how to handle those constraints? So all this, is more like domain expertise meeting machine learning. Okay. So I will not get into the details of any of this. All I wanted to say was, with this example, was to show that there's a nice way, if you have expertise in some domain, it could be finance, it's healthcare, anything else, transportation in this example, but you can always see, okay, I know this, and I have seen some tools in the class, or tools, in the syllabus page. If there's a way to match them and use them, that would be a good example. That way you can really stretch the boundary of, you already know how to perhaps do this assignment. In this case, the team already knew how to match crowdsources to requests using other techniques, what are called heuristics in this area, meta heuristics. Instead of that, they used machine learning approach. Okay, I mean, if you look at the network, it's actually just 2 fully connected networks, 2 fully connected layers, 3 fully connected layers, and that's it. So the model is not hard here. The hard is just they're matching the domain expert, so domain specific details to a neural network problem. Okay. And since it's not supervised learning problem, there's some extra details of what is the loss function and so on. But it's all not new, in the sense, once they match the problem to this deep reinforcement learning setting, the objective, how do you, like, what is the gradient descent approach there, and what is the specification, everything is well known. Okay. So that's example one. I wanted to show two examples from our department, a couple of PhD students working on this, working with me actually, just to give you a sense of, some other project ideas. Not to, these are not projects which are like extremely complicated, but giving a sense of. So here's a project with Son. I don't know how many of you met Son, but okay, nobody has met Son. Okay. Son is a student in the department.
Does it TA?
Yeah. So this is a work that we wrote, but it's not really at the project level since we have kind of gone beyond that. But I wanted to give you the idea here. Okay. So the idea is basically that most large language models today, like a good chunk of popular language models, they are the companies behind them, especially if they're proprietary or even the open source one, the folks who release them take some effort to kind of tune them beyond just doing a language modeling optimization problem that we have seen. Like some of you guys have done it. I mean, you guys have done it, a version of it with LSTMs in the assignment, but you can build a language model with transformers. Okay, we have not seen the architecture in the class. We've seen a translation related encoder decoder architecture in the class, but you can build a transformer-based model to just predict the next word. Okay, that's the kind of basis for many of the models. So in this work, what we did is basically, when there is a need for further kind of curtailing the outputs of the model to kind of ensure that it doesn't go completely off the good paths and like kind of deviate from the good outputs. There's a need to further tune it using various approaches, basically using human annotated data. Okay, so to simplify this, all I'm saying is that once you train a transformer-based model with large corpus, very simple, just like all the other models we've trained, after that, there's a next step where you can use human annotated data to further tune it. Okay, what is this human annotated data? It's basically you can give an input to like a prompt to the LLM, you get some responses, and you ask the humans to rate the responses. Hey, is response 1 better, response 2 better, response 3 better? Remember, language models, I mean, even with Markov models, you can always sample and generate different next set of tokens or next set of words given the same starting outputs, right? Same thing with any other language model. Like the moment you have distribution over vocab words, you can always sample, or you can take the second one instead of the top one and generate multiple responses. And then what many companies at least did, and even recently they're doing it, is basically give these responses to a bunch of human labelers and ask them, hey, which of these responses is correct? Okay, give them some sort of a ranking or priority or preference, and then use that preference data to further tune your LLM so that it can generate, maybe the best response is actually a fourth one and not the first one. Then you want to ensure that the fourth one is actually the one generated when it's actually live, when a lot of people are using it. Okay. So that's the context. And the idea in this work is just to how to deal with that preference data. What if the preference data is corrupted? Okay, what if the labelers just arbitrarily chose, okay, I prefer fifth one instead of first one, because they're not, maybe their incentives are such that they just are paid by every response they give and not really the quality of response, for example. Then what if the input data is corrupted? Okay? And so this draft that we just, I guess, I don't know if there's a picture. Yeah, there's a picture. Let's use this. So what we're trying to do is basically, if there's a raw preference data, which is that humans have said, oh, A is better than B or C is better than D, and so on, like A, B, and C being just responses of an LLM, then there's a step, this blue step, which will not go into detail, but just to give you a project idea, there's a step that we do so that we can correct that preference data. Okay, just somehow fix that preference data, even if there are like changes in like if out of 10 labelers that are helping us, one of them is like completely rogue, okay, or completely giving wrong, kind of incorrect preferences, then still we can deal with it by cleaning up the data and then passing it on to the actual tuning step. And tuning step here, there's some acronyms here, but don't worry about it. It's just a tuning of an LLM. And then the question is, if you use raw data with the kind of corrupted or bad preferences, then there'll be some tuned LLM. And if you actually kind of clean the data, and then tune the LLM, then there'll be some other LLM. And then you can see what is the difference in terms of an appropriate performance metric. Okay, like helpfulness or various things like, how often is it going off the, right trajectory. You can check that. Okay. So what is so although there are a lot of details specific to LLM here, think of a, like even CNNs, right? So you have your data, CIFAR-10 data that you trained and you got some performance. What if I arbitrarily corrupt, change the labels? Okay, you can do that, right? You have for every image, you have a label. You can just like flip a coin, and with 5% probability or 20% probability, you change the label to some arbitrary choice. Now you have a corrupted CIFAR-10 data set. Now you use that to train or fine tune whatever, transfer learning, whatever your model. You can always check how does the corruption influence the degradation of your model compared to like the cleanest model, right? So this is just an example of kind of understand how corruption influences downstream effects, and also if you have a way to resolve it. Okay, there are some ideas there, and some actually companies which are trying to resolve data quality before it's ingested into machine learning models. It could be vision models, it could be LLMs, and so that's another project idea. Any questions here about?
Is it about the problem of noise in initial data and how to overcome that?
Yeah, but the noise is supposed to be like what is called adversarial noise, as in it's a noise where you're not thinking about statistical noise. You're talking about somebody arbitrarily like giving bad answers. Yeah. Yeah, and by the way, labeling is a big chunk of this machine learning world, which we don't get exposed to in our courses. But maybe you in natural language applications with LLMs, maybe the labeling effort is reduced. But there is actually at least for tabular data, for example, if there's any labeling needed, or for other vision and text data, which is like too domain specific and it's not like general language or general vision, then a lot of companies employ a huge set of annotators to actually annotate your data. Okay, it's a big industry by itself also. For example, big social networks use labelers for content moderation, for example. Okay, these are all big organizations. So this is about this. And the second example of a project, this is another nice application by another student in the department. It's about recommendations. Okay, so I don't know how many of you are into marketing, but the idea is pretty straightforward. So let me just. So the idea is, how do recommendations work today? Okay, recommendations work. Recommendation, like if you go to an e-commerce website like Amazon or elsewhere, I'm just simplifying most of it, by the way, is that there's a apparatus or infrastructure for them to log every event that happens on the browser, right? The browser or whichever device you're seeing the recommendations in. They log all that information of, oh, user did this, user went from product A to product B, they spent 5 minutes on looking at the reviews, and then they did a checkout and whatnot. So all that information is logged in what are called, we're just calling it web logs. Okay. And then you can, curate that web logs, and then you can create user profiles. You can slice and dice the data, EDA, whatever, create embeddings of your products and whatnot. And then, as a part of that, you also build a recommendation model. Okay, oh, if people are seeing this, perhaps, and there's a bunch of people seeing the same type of thing, these types of ideas you might have heard of, a bunch of people are seeing the same type of things, then for that person, perhaps we should recommend the things that some of the other people have also seen. If they're similar, then they might like similar products. So you can build a recommendation model like that, or there are many approaches. And by the way, these recommendation models also use transformer model blocks or LSTM blocks, or any of the blocks that we've seen, okay, fully connected layers and so on. So it's basically the same idea. So that's what happens here. And this project was talking about, okay, today we know that there is LLMs, large language models, but there are also what are called visual language models also. Okay, so which in fact, models which can answer questions related to a image. So if you give an image and say, hey, what is in that image? I think it's visual question answering was the example we used when we were introducing NLP. But so when given an image, some of these LLMs have been trained such that they can work with image tokens as well, not just the text tokens. Remember, text tokens of words can be mapped to integers. Similarly, image can also be somehow mapped to some integers are basically not integers, but you can actually get their embeddings, and we know how to get their embeddings. So there's this notion of using both to kind of say what the image is about and things like that. Okay? So this project is about saying, okay, we're going to collect user interaction data from the website of the e-commerce website, not through logging, through like carefully logging every event with a timestamp, but just taking a bunch of screenshots. Okay, take a bunch of screenshots, and then just pass these screenshots to a vision language multimodal LLM. I guess MLLM is just multimodal LLM, and just ask what is going on with the screenshots. Like what is the user doing through the screenshots, right? And so you don't want to ask a very generic question. You do some prompt engineering to say, hey, what is something actionable that I can take away from looking at these screenshots? Okay, from the platform's perspective. And then maybe the LLM is able to say, okay, hey, the user's looking at green colored trousers or whatnot, right? So something specific, so that way you get information that, okay, in this current session, the user is focused on X or Y or Z, and then use that information to kind of pair with the potentially recommendation model, or just use the LLM to also kind of make the recommendation. It's just a very simple idea. Although, obviously this is a long report, but the core idea is simple. Here's a pre-trained model, and the pre-trained model has some extra capability, which is vision. How do I use that in an application, which is e-commerce or marketing in this case? Okay, so it's although there's a lot of text, if you look at the finished product, it looks pretty complicated. All the three examples that I gave, but the core ideas are actually, the starting kernel is actually pretty intuitive and simple, especially if you're in the domains. If you're in marketing, it makes I mean, even if you're not in marketing, this makes quite a bit of sense. Okay. Any questions here? No. Okay. If not, I wanted to kind of show two things before, which are not related to the project. So this is the end of the project section. Two things that happened in this past week before just jumping into our content. The first thing, I don't have the paper. I should have opened the paper. This is a paper called The Era of One-Bit LLMs. Okay. LLMs are just, think of them as transformer models. Okay, so since we have covered transformers, it's just some pre-trained transformer architecture. And the paper is this work by folks from Microsoft is just saying that they created a new model, some model name, where every single parameter, right? So the W or B or appropriate parameter is ternary. Okay, so it's just taking a value 0, -1, or +1. Okay? So instead of the weights taking arbitrary values, and that's what we've been thinking about, because we do gradient descent, and so numbers will change. They're real numbers. Instead, they in this case they train such that these numbers are only between these three values, and they're saying that given that, they're actually able to see really good performance in terms of performance metrics. Okay, and this is where we'll have to get into details, perplexity, and some other names here. Compared to existing what are called full precision or floating point 16 or variations. So full precision is what we've been generally work with. So they're just saying that even with this restriction, the same architecture trained in a different way can really match the performance of full precision models. Okay, this is new work, and what is the impact of this work is LLMs, at least for inference, if you can just work with 1 bit or a little bit more than 1 bit compared to 16-bit representation. So you really compress the model already by 16 times. Okay, something which needed 16 GB could just need 1 GB of space. Okay? So it's a big, it's a good advancement, but there are a lot of advancements happening every week. The second one is actually something called stable diffusion. I don't know how many of you have heard of stable diffusion or image generation models, DALI, Open AI DALI, where you write text prompt and then you generate an image. Okay, so I guess then we'll look at this, but this is a paper that they wrote, which is called, I guess, Stable Diffusion 3. So they have had multiple versions of this approach, and they're not the only ones. I mean, obviously, there are multiple groups which have used some type of what are called diffusion models, okay, which we have not seen. But the diffusion models are defined in terms of transformer blocks. Again, okay, the same transformer block we've been talking about for the past 2 weeks, same blocks, to create this text to speech, text to image generation. Okay, that's the use case. And the advancement here is that they have kind of taken care of the text part separately. That was the advancement from previous work. And by doing that, what they achieve is basically like if you ask the prompt, okay, go with the flow with some colorful background, appropriate. I mean, I'm not telling them exact prompt because you can see it in the paper, but you can actually get the text correct. Okay. Previously, if you ask to embed a text or a string in an image, you would miss some letters. Okay. So the big advancement here is that they have gotten the text correctly in the generation process. Actually, there may be a, let's see. Maybe not in this. Yeah, you can. So this is the, for example, you can see this smiling cartoon dog sits at a table, coffee mug on hand as a room goes up in flames. This is fine. The dog assures himself. And so you get the right text. Okay. First of all, I mean, obviously the generation itself is also a big deal compared to 1 or 2 years ago, or even 3 years ago. But in addition to the generation, they are able to get the text correctly. And obviously there are many other enhancements. So this is I guess, a big delta from before. Any questions about this whole section? I know this is kind of superficial. We didn't get into any detail, but the next, next we'll get into details of what we've been talking about. Any questions about the projects or? Okay. So before I get into VAEs, I'm going to talk about, just want to have one last comment about this, is that this generation of images is exactly what VAEs will do. And this is exactly what GANs will also do. Okay. So GANs, VAEs, and diffusion models, which is Stable Diffusion is one of them. They all are about generating from noise, sampling a new image from basically nothing or noise. Okay. So this, so we'll cover 2 of them, VAEs and GANs, but diffusion models are in the same category. It's just that we're not covering them. At least that's not the plan for today, but they're all in the same category. So this one has a connection to that. And here's another, so GANs, right? So we'll talk about GANs in a second. There's a website called thispersondoesnotexist.com. Okay. I don't know if you've seen this website before, but if you refresh, they regenerate an image. So at the very bottom, actually, I don't know if you can see it. It says StyleGAN2. Okay. That's the name of the model. Actually, I don't know if there's text. Okay. So the StyleGAN2 is the name of the model that generated this. Okay. So obviously, you may say, okay, is this person actually from a database, or is this person actually synthetically generated? There's always, the more and more realistic you have this images, then it's unclear, right? But at least that was the, I mean, you can look at the paper, StyleGAN2, and maybe we'll look at it when we get there. But this is the second model that we're going to look at today. Okay, so today we'll not look at diffusion models, although I showed you Stable Diffusion 3 paper. We'll look at GANs, but not StyleGAN. We'll look at GANs, what's the canonical GAN architecture, and StyleGAN is like an extension to that. And we'll look at variational autoencoders as well. So, okay, so at least hopefully that gives you some interest. So where are we in terms of our trajectory? We may be going slow, so we may have to cut off some material towards the end, but we'll kind of continue our work, kind of look at variational autoencoder today, and we'll also talk about generative adversarial networks today. So that's really the goal for today. So in terms of takeaways from after going through this session, is obviously we want to get a sense of what are variational autoencoders. We looked at autoencoders last time, but we'll look at what are variational autoencoders and why are, what does variational mean and what do they do? We'll look at it today. And then we also want to get the intuition behind GANs, okay, generative adversarial networks. What's changing here is that so far you've been looking at supervised learning with cross-entropy loss. Okay, whether it's sequence models or whatnot, they all eventually there's Gaussian gradient loss. Here now we'll have to talk about, since we are doing unsupervised learning, we need to define an appropriate objective function. Okay, so we'll look at so there's going to be the model architecture and the objective function. That's going to be the two things that we're going to look at. Okay? We'll also wrap up with what is the difference between GANs and VAEs. But as I said, in this category, we also have diffusion models. It's just that it's not covered in the syllabus, but it's the same idea. So if you think of diffusion models, you can think of GANs, VAEs, they're all in the same category. Okay? They all are just trying to sample some pretty complex thing, like an image, realistic looking image from an object, which is trained on some training data. But the sampling is such that you're not just looking up a existing image from the data. You're just trying to create a new image. Okay? Okay, so let's start with a brief recap about autoencoder. We have just training data, which is a bunch of images. Most of our discussion today will be about images, but you can do that for other situations as well. So what is the objective? It's unsupervised learning problem. We have a bunch of images in the first setting, which is the warm-up setting, autoencoder setting. All we want to do is compress that data. Okay, it's like projecting the data into low dimensions. If you think of PCA, you're kind of reducing the number of columns in your raw data, right? So here we are trying to do the same. We're going to compress the information in the training data. Okay, and so how are we going to do that? As the word auto and encode suggests, we're going to take an input data point, through a neural network, bring it down into some lower dimensional space. This is called the latent space. I guess this step is called encoding. And then once you have the Z, you want to have another neural network which projects it back into higher dimensional space. And therefore, now you can say that without even a label, I can say, okay, how far is the X from X hat? And tune my parameters of the decoder neural network and the encoder neural network so that I can do really good reconstruction. And if I can do really good reconstruction, and if the feature space, the Z vector, for example, is much smaller in dimension than the X's, then I have really compressed the data, right? So for every X, I can have a smaller Z. It's like the same thing with PCA, right? For every original raw data vector, I have a smaller, collection of principal component values, for example. Okay. So that's the idea here. To autoencode is just just means yourself. So it's just comparing X to X hat to your own reconstruction. And then I'm encoding my data to an appropriate low dimensional space. Okay. So this is what we did last time. Any questions about this? Don't worry about the larger dimension. That's denoising autoencoder is just a variation of it. Any questions here? Okay, so same picture zoomed in. The loss function generally is a squared loss. Okay, so at this point, yeah, I guess only one takeaway is that there are no labels needed. This can also be compared to PCA, as I just mentioned. In fact, if you use a no hidden layer neural network for the encoder, like a fully feed-forward neural network, but no hidden layer, so it's just literally just a W on B, and then in fact, no, you can drop the B also, and then another W matrix here to bring it back in a higher dimension. Then that would be the W here would be like the PCA's U matrix. Okay, so it's basically the same as PCA, except that you're not ensuring that the there are no principal common directions that are orthogonal here. Okay, so you could have a representation where these like you could have, if you want to think of basis directions, you could have directions which are not orthogonal. So you could have like aligned, 30 degrees, angle between directions, for example. Okay. So anyway, that's the relation to PCA. But this architecture is not about, it's not really about generating new samples. Remember the whole unsupervised learning, motivation earlier when we talked about last time was there was obviously dimensional reduction use case. We mentioned that as one of the use cases. That makes sense for autoencoder, but we are now actually exclusively talking about sampling And that's where we said, okay, sampling has uses. We can think of new, we can use it in creative use cases, or we can just plan. If you can sample data, then we don't have to explicitly represent distributions. We can actually directly work with samples. Okay, and so in that use case, we don't really care about dimensional reduction itself. Okay, all we care about is, our primary objective is to sample, and this doesn't help us sample. Okay. Because it's all about compressing data into low dimension. You cannot say, you cannot say, okay, if I define a new Z and project it up, into a higher dimension, is that new point actually going to look like, let's say I have a bunch of cat images and I all compress them into 10-dimensional vectors. If I slightly burn up the 10-dimensional vector and then recreate an image, it may not look like a cat image. Okay? That's because this is all about compression. It's not really about sampling generation. Okay? And that's where the next architecture comes. Since the previous architecture was a warm-up, this next architecture is all about sampling. Okay, it's called a variational order encoder. And so we'll see what this term variational means. Variational just means optimization. Okay, it's another word for optimization. And so why is there a word explicitly about optimization? Even the previous warm-up thing had an optimization, some L2 mean square error minimization. That's because you'll see that the way this model is defined is through a graphical model, okay, as a probabilistic graphical model, which means there are going to be random variables, which means there's going to be some likelihood type of an expression. And since there's a likelihood type of an expression, you can either directly optimize the likelihood, or in this case, there is the reason why they talk about have this word variation is because whatever the likelihood type of expression is, they're gonna kind of create an approximating objective function, and that's what they'll maximize. Okay? And so that approximating function is what leads to the word variation. Okay? So they're not instead of directly optimizing likelihood, they do some tricks. I will see those tricks actually pretty transparently, but and so that leads to the extra adjective then. Okay, so what is the idea? So the idea is we kind of want to build on the previous architecture. There's a X input that goes to the Z, and then Z creates an X prime, X tilde. What we want to do is now start thinking of random variables. So we want to think of X as a random variable. We want to think of Z as a random variable. So it was not the case before. So previously it was just a bunch of data, just project it down, project it up. Okay, there's no notion of a random variables. Okay. Here now we're going to talk about X and Z as X and Z as random variables, and then we also want to make Z a Gaussian random variable. Okay? We want to make Z a Gaussian random variable. Why Gaussian? I mean, it could be any parametric distribution, but we want to make it Gaussian so that what we want to do is eventually the decoder part where Z goes to X hat, basically. If we can sample Gaussians and we can pass it to the decoder, we can get new images. That's the idea. Okay. So we want to have a very clean story of, oh, if Z is a Gaussian random variable, I can sample new Gaussian, realizations. And if I pass it through the decoder, I might get new images, for example. Okay. So there are going to be a couple of changes needed. One is the architecture level. The architecture is going to look like almost the same, but now since things are random variables, there has to be some randomness captured. And so there's going to be a slight change in architecture, and there's also going to be a change in loss function. But that's, you might say it's slight. I said it's slight changes, but actually the whole narrative has changed. Now things are random variables. So you can actually have a very principled way of defining what is the objective and so on, instead of just thinking of reconstruction error. Okay, so let's talk about the loss. So loss as a teaser, and we'll see how this comes about, will be sum of two things. It's going to be the reconstruction loss from before. I'm just talking about the final output. We'll see why it is like that. It's going to be a reconstruction loss, which is the loss over X and X hat, like how far X hat is from X, okay, in my training data point, training set. But there's also going to be another term, which is called the latent loss. There's going to be something about Z's and how far Z's are from like a Gaussian distribution, from a Gaussian distribution. So it's not directly on Z's, but the distribution that we prefer, which is the Gaussian distribution, and the distribution we get by tuning the parameters of the encoder. Okay, so what is intuitively happening is that now since X's and Z's are random variables, you can say X's are passing through a deterministic thing, which is the encoder, right? So there's some parameters in the neural network. So think of it as like transforming a random variable to another random variable. If you do that transformation, you'll get some transformed random variable, but it's not expected to be Gaussian. So there may be a difference. Okay, that difference is what we want to minimize in the latent space, in the Z space. Okay. So we'll look at the kind of intuition. So all I'm trying to, in this slide, all I want to motivate is that the objective function now is well motivated, and it's going to be, there's going to be reconstruction error, reconstruction loss, and also a loss in the latent space. Latent space is the Z space. Latent mostly because you don't observe Z's in reality. So our data set is just X's. Okay. So that's on the loss, commentary on the loss. We'll come back to the loss in a second to kind of see why it is the case and why the name variational comes. The architecture involves also a change, which is that it involves now a sampling in between. Okay? So what is the sampling? So I have the original cat image. I do the encoding. Okay. I need to get to Z. Instead of getting to a single Z vector, what I'm going to do is generate 2 vectors. Okay. I mean, you can always say I generate a single vector and just call the first 5 coordinates the mean vector and the next 5 coordinates the standard deviation vector. But basically, I want to think in terms of, okay, when I encode, I'm going to generate 2 vectors. And in fact, I'm going to call them the mean vector and the standard deviation vector. Okay. Why mean and standard deviation vector? Because you can think that, okay, with mean and standard deviation vector, I do have a candidate Gaussian distribution with the mean vector being the mean and the standard deviation vector characterizing the diagonal of the covariance matrix. Okay. Right. I will have these. And then because I have the mean and the standard deviation, I have a Gaussian distribution from which I can sample. Okay. I'll sample a vector, and that vector is what I'll pass it through the decoder to try to reconstruct my image. Okay. Now you can imagine that if I choose so previously, if you remember, I was encoding, getting a single vector, and the same vector was, that vector was being passed ahead, and I was doing reconstruction. By doing the sampling step, I'm making the problem harder. Okay. No matter what the sample is, I still have to reconstruct what I had in my training data. So which is a harder problem. Right? But this is actually also the part where you can imagine after training, I only have to look at from this green, vector onwards. I can generate a new vector every time because remember, I want to impose the fact that on the latent space, the distribution is Gaussian. So I can always sample a new Gaussian, pass it to the decoder, and I can get an image. And hopefully those images are generalized in the sense that it's not just remembering or compressing the original data, but we can potentially get new images, and those images are as realistic looking as the training data images. Okay, that's the idea. So, you think that, okay, how does it how does it influence backpropagation? It doesn't, because once you have a realized sample, you can always backprop appropriately. So there's no even though in the forward pass there is a sampling step, in the backward pass things you don't have to kind of navigate around any sampling. There's no issue with backprop here. Any questions? Let's before talking about backprop, we need to talk about the loss. And so let's come back to the loss because the loss is a new thing. So remember, up to most of supervised learning, we have not been focusing on loss at all. It's just cross entropy loss. That's what you did in your assignments also, or binary cross entropy, whichever you chose. So we want to kind of this is the first time we'll see a kind of slightly different loss function. Okay? And we'll also see another loss function later on when we talk about GANs. Okay, so as I said, this sampling is what is allowing for generalization. So Gaussian noise ensures that we're not remembering only the training data. Okay? So we're not just remembering and just focused on compressing. Okay, so here's some examples before we get into kind of discussing the loss in a little bit more detail. So here's the MNIST data set, where forget about the labels now. I mean, we're saying, okay, here's a bunch of images, and we can train this VAE so that it can generate new MNIST images. Okay, so all you're seeing is basically samples generated from the original data. So I guess this is the original data, and these are samples being generated. Okay, so as you're training more and more, they're just stopping at any given point and talking about, okay, if I randomly give an input, give a random Gaussian realization as input to the decoder, what MNIST image is generating, you can just see that these are the images. Initially, you're getting bad images, but you're kind of getting kind of newly generated images. Okay. So let's talk about the loss a little bit more, right? So as I said, really the starting point is that these are Gaussian, these are random variables. Okay, so X is a random variable, Z is a random variable. Since there are two random variables, there's going to be a joint distribution between them, P of X comma Z. Okay, and any joint distribution between two random variables, you can write it as the conditional probability of X given Z times probability of Z. So this is just the law, this times this is just a joint distribution of X and Z. Okay, so there's no assumption anywhere. It's just the definition. And let's say theta star is the true parameter of this joint distribution. Okay, so if you know theta star, you can sample X comma Z pairs, and so X hopefully looks like an image, Z can be whatever vector. Okay, that's the conceptual idea. In particular, we are splitting it this way because we know that our generative process. Remember, graphical models are generative models, and so there's generative description to this thing, which is like sample is Z, which is the sampling Gaussian, pass it through the decoder, and you can get a realization of and then samples from whatever you get here, you get a realization of X. So in the sense that you sample Z first, and then you sample X next. Okay, in the generative description, and that corresponds to the VAE architecture that you saw. Okay. Any questions here?
Could you explain the conditional probability and how that helps us with it?
How that helps us. So variational encoders are by definition probabilistic graphical models, which just means that we think of everything as random variables, and since X and Z are the only things of interest in our description, we didn't introduce anything else. Maybe X tilde, but it's the same thing. We need to kind of set a joint distribution between them, and that's, let's call it P theta star of X comma Z. But instead of explicitly saying that, we're saying P theta star of Z and P theta of X given Z, because this product is the same as that joint distribution. Okay. Now, why are we going this route? Is the whole point is that in autoencoder, we are just focusing on compression, like PCA. It's just about dimensional reduction, but we care about sampling. Okay. If you have a graphical model, if you have random variables, then we can do samples. Okay. So there's an explicit joint distribution here. And so we can sample from Z, which we want to impose as Gaussian. And then if we sample from Z, pass it to a decoder, then we can sample at X. Okay, that's sampling is a motivation for introducing this notion of random variables and talking about joint distribution and so on. Okay, that's the motivation. So we do need a joint distribution, or we do need distributional representations here because we do need to sample. Any other question? Okay. So for that, we want to say P of Z, we want to impose it as Gaussian. Okay. Why? Because we have the degree of freedom. Our data set is only X's. Okay. We don't know what the distribution of X is. Okay. At least the marginal distribution of X's, because there's just a bunch of images. But Z's are not given. What if we prefer? So that's a degree of freedom, right? We can always prefer Z to be some distribution, because if we prefer some distribution, then hopefully the encoder ensures that you go from an unknown distribution to the preferred distribution. Okay, so we're going to assume P of Z to be Gaussian, and P of X given Z to be the decoder, which is what we're talking about. So given Z, we go through the decoder, and that hopefully characterizes the conditional probability of X given Z. Okay. So these are our assumptions. And what do we observe? We only have the data, which is X's. Okay. So given these two assumptions, given these two assumptions, what is P theta of X, right? So P theta of X is the marginal distribution on X, or just a distribution on X, that given can be written in terms of these two, right? So P theta of X is P theta of Z times P theta of X given Z. This is just the joint distribution between X and Z. I want to integrate out Z. If you integrate out Z, then you are left with distribution of X, right? So the third point all we're saying is, I want to assume these two. One is PZ is Gaussian. Second one is the conditional probability of X given Z is just a neural network. Okay. Given these two, I can write the data likelihood, which is what P of X is, which is the probability of X, is likelihood of the data, because x's are what I see, you need to integrate out these two quantities, where P of Z we are assuming is Gaussian, the other one is a neural network. Okay. Now this is actually pretty hard to do. Maximize the likelihood of my data, which is maximizing this integral form, is hard to do. And that's why we kind of do some steps so that we have some sort of a optimization objective. Because otherwise, this is our optimization objective. Change the network parameters, like this theta kind of represents the network parameters. Change the network parameters such that you maximize the likelihood of the data. Okay? It's just that this expression, this objective doesn't look like any cross entropy loss, anything like that. Okay, and so we want to kind of fix that, and that's the next couple of discussion points will be about that. But if you're not comfortable with this, next couple of slides will look like a mess. So I want you to ensure that if there are any questions, please let me know. Okay, so what we want to do is maximize the likelihood of the data, P of X. We just don't want to work with this expression. Okay, that's the idea. And how do we kind of massage that expression and do something so that we can actually have something like cross entropy loss? In fact, I already told you what we want to get. Eventually, what we'll get is some sort of reconstruction error and a latent space, some sort of a loss between the latent, like what we prefer and what we generally get from the encoder side parameters. Okay, so let's do that. So to do that, what we'll do is a small trick. We're gonna make the encoder also probabilistic, which means what is that? It's just a this become clearer when we go through the derivation. But basically, we'll say let's have another neural network that's going to capture the condition probability of Z given X. Okay? So far in our graphical model, there is no Z given X. We only have P of Z and P of X given Z. Okay, that's our model. But now we want to get into the implementation of how to maximize this objective. That's more of a computational problem. Since we have a computational issue, now we're going to define a auxiliary, like an extra network, which is literally the encoder, and now talk about the encoder kind of approximating the condition probability of Z given X. Okay? And this will become handy in our defining of our objective function. Okay? That's the idea. But in the model definition, it's just two random variables X and Z. And the way we decompose it is we want to ensure Z is Gaussian and X given Z is just the decoder part. Okay, so in the model definition, there's no encoder, but we're going to introduce the encoder like this. Okay, so this is exactly what we saw before. So X is going to give you a mean vector and a covariance or standard deviation vector. And using those two, you can sample a Z, and that can be passed towards the decoder. Okay, this is exactly the same as it's just shown in a way where the network is gone. It's just talking about, okay, here's the mean, here's the covariance, or here's the standard deviation. Okay. The right-hand side is exactly right-hand side is what we did just define in the previous slide, where given Z, hopefully Z is Gaussian, we're gonna create an X. Okay, so how do we create an X? Go through the decoder. Decoder is just a decon network, right? It goes from a vector to an image. Instead of an image, we're gonna have first a mean image or a mean vector and a standard deviation vector. Again, image space, it looks like a mean of like a bunch of mean values, like a mean image and the standard deviation of those mean images, and then you can get an actual image. Okay, so this is just an extra randomization that's introduced at the decoder output. Okay, otherwise the decoder, there's no extra randomness to the X. If Z is the only randomness, then X is not, X is like a deterministic function of Z, then X is really not random. Okay, condition on Z. So we want to make X still random even if Z is given, and so that's why there's an extra mu and sigma. So this trick is just to, when you create an output of a network, you can just think of the output as like split into two parts, where one part, first 5 coordinates or first half is just mean, and the second coordinate or second part is just covariance. Okay? So it's a very natural trick. Any questions here? So far it's pictures. The next slide will not be pictures. So I want to okay. So far, just to summarize this slide, right-hand side is what we have defined in a model. Left-hand side is some extra thing that will help us deal with the objective function. Okay. in fact, it's also part of our training to have this extra apparatus, which is the encoder. Otherwise, the model just has a Z random, a Gaussian random, just a decoder, and X's. Okay, that's the model definition. Okay. So before defining the loss function, because I said there's a reconstruction error, that's fine, but there's also latent loss, and I want to capture the latent loss. So we want to kind of define it properly. For that, it's defined in terms of what is called KL divergence. Okay. KL divergence stands for okay, I'm kind of missing the expansion, but it basically is defined in this way. Okay, so it's just a sum over x's, all the values that x can take, p of x times log of p of x divided by q of x. Okay, so it's some sort of a dissimilarity between two distributions, and the expression that I've written here is for discrete distributions, so the distributions which are like take finite values, like if you have a probability mass function. Okay? So how do we, so this is the notion of dissimilarity between distributions, but before that, this, so this is just a very, very short bunch of definitions that are kind of part of a field called information theory. I don't know if anybody has heard of information theory. Any electrical engineers here by training or undergrad? No? Information theory is a part of electrical engineering, also applied math, but kind of that's what leads to a really good, really good wireless systems like your phones, and you're able to hear crystal clear voice from contacts and multiple miles away, right? Thousands of miles away. That's all thanks to understanding really well the physical systems of how signals work, but also how to ensure that signals can be transmitted and so on. So, okay, for example, so that's some of the impact of this work, this whole field of information theory. You can also think of zip utilities like zipping up data, compressing data. That's also related to information theory. Okay, so lot of impact in the world. So what they do is basically work with distributions. Okay, let's say probability mass functions, and they define information, a quantity called information, to be negative log of the probability of particular value. Okay, particular value a random variable can take. Okay, so basically what is this is it's very similar to the cross entropy loss kind of term. Basically, information is a quantity where if the probability of x is low, then the negative log of that probability, like if probability is low, let's say it's kind of 10 to the power minus 3 or something, then the negative log of that value is going to be 3 units, right? So 10 to the power minus 3, and there's a minus in the front. So log, let's say log is base 10, then it's 3 units, right? Whereas if x is really high, x, there's a, so probability of certain other value of x, let's say it's really high. Let's say it's almost close to 1. Then log of 1 is close to 0. Okay? So all I'm saying is if there's a outcome which is very likely, there's not much information in that. And if an outcome is very unlikely, there's a lot of information in that if that realizes. Okay? So they're just trying to say quantify what is kind of, what is the different information, I guess some sort of magnitude. They're just saying that if an outcome is too likely, then that information content is low. If the outcome is not too likely, information content is high. Is an interpretation that we can give. And then entropy is just the average of this information quantity. Okay, so you can take a negative log p of x, then you can just think of this as sum over p of x of this negative log of p of x is like the average information in this random variable, or the distribution of this random variable. So think of a random variable which is like, let's say it's just a binary random variable, which has with probability like 0.9, it takes value 0, and with probability 0.1, it takes a value 1. Okay, so it's lopsided, right? So there's a high probability of one of the outcomes happening and very low probability of the other side happening. On average, okay, the information content is low, okay, for this type of random variable. Why? Because there is a good chance that it's going to be 1, and we know that with high probability it's going to be 1, and with that probability we know that information content is low if that outcome happens, right? Now compare that to another binary random variable, this time a fair coin toss. So it's 50% chance of being heads and 50% chance of being tails. Then the average here is going to be higher. The average information content is going to be higher than the previous case. Okay. Why? Because a priori it's either heads or tails. It's going to kind of be something that you could not be predict. You can't predict. Whereas in the first case, you can say, oh, most likely it's going to be 0. Okay? And that's why, for example, you can say the distribution that maximizes entropy is the uniform distribution, or the distribution which assigns equal masses to both outcomes. In this case, you might have used entropy if you've done decision trees as a rule for splitting. Splitting nodes. Yeah, so that's exactly the same idea. So here we are just talking in terms of information content of an outcome, and then the average information content of the distribution, as captured in the distribution of a random variable. That's entropy. And KL divergence looks like that expression of two different quantities. It's like if you split this term up, log of A divided by B is actually log A minus log B, right? And so you can see the first term to be the negative entropy of it's like minus P of X log P of X. Right? If you put a minus, then it's the minus entropy of X, right? And then there is a cross entropy type of a term as the second term. So all I'm saying is KL divergence is some sort of a difference between average information content between X, but X's distribution being P and X's distribution being Q, approximately. Okay.
Could you explain this expression of the
KL divergence?
Yeah.
So there's actually
what's the Q of X? Is it
Q of X is another distribution defined on the same X. Right. For example, in my binary random variable case, let's think of P of X as being 0.9 for outcome 0 and 0.1 for outcome 1. Then Q of X could be, as an example, 0.5 for outcome 0, 0.5 for outcome 1. So there are two probability mass functions defined on the same support, like 0 and 1 as the two outcomes that can happen. So those two probability mass functions are comparable. And this scale divergence, all is saying is how different are they? Okay. So for example, if P and Q are the same, you can just see that log of P by Q, if it's like P by P, then log of 1 is always 0, then there's no, they're not dissimilar. So let's think of like some sort of a distance measure. So if Q is the same as P, distance measure is 0. If P and Q are very different, then distance measure is going to be some large positive quantity. Okay.
How does that person optimization or
so we'll see. So the reason why I introduced this as an aside or back to the basics is because this term is going to be part of your objective function later on. Okay? This type of term will be part of the objective function. So actually, let me show a picture. So here's an example in one dimension. Okay, just to try to let's just focus on one figure. Okay, which is if I have it in the previous slide. No. So let's focus on one of the figures. Okay, the difference between figures is subtle. Before understanding the difference between the figures, let's focus on one of the figures, left side figure. So P of X, let's say there's a P of X, which is this bimodal distribution. Okay, so this DKL P comma Q is this distance measure between P and any arbitrary Q. And if you want to minimize this distance, okay, you want to find the best Q. Okay, best Q that minimizes the distance between P and Q. Okay, that's an optimization problem. Okay, and let's say that best Q is Q star. Here, in one dimension, we're just showing what is the best Q that optimizes for that minimizes the distance between P and Q. So P is given; it's just data. This blue curve is given, and you're asking, hey, give me the best Q in terms of minimizing the KL divergence between P and Q. Then the best Q happens to be this one. Okay, why is this one the best Q? Is because if you recall the definition of KL divergence, is the average of P log P by Q. Okay, so you just want to ensure that whenever P is present, as in P has a positive mass, you want to definitely ensure that Q has a positive mass. Okay, if Q doesn't have a positive mass, there, let's say Q is 0, then it's like something divided by 0 is like a huge number. Okay, and so we want to remember we want to minimize the KL level. So we want to ensure that wherever there's a positive mass, we want to ensure that Q has a positive mass. Okay, and so it turns out that this is the way to do it. Okay, so I did not actually, one key important point I did not mention, otherwise why wouldn't Q be exactly the same as P, is that we want to ensure that Q is a Gaussian. Okay, we are restricting our Qs to be one-dimensional Gaussians. Okay, so if given this data point, which is not a Gaussian, we want to find the closest Gaussian distribution by minimizing this KL divergence, then this is the Gaussian that we get because Q is in the denominator. Okay, but if you flip the objective and say, hey, I want to, and still P is still the data, but now I say, hey, Q is in the numerator, then tell me what's the best fitting Gaussian, which you can also do. Okay, so where you can just say that the P is given as usual, but P appears in the denominator now. Then the best Gaussian is just the Gaussian where is like this, which is the green curve here, where if basically what's happening is Q is in the numerator. So we want to ensure that we don't care where P has positive mass, because even if I set Q to be 0, that term is not gonna blow up. But we want to ensure that we want to be as large, as far away from Q at any given point of any given value of X, in the sense that let's say since Q is positive here, for these values of X's, we want to ensure that Q of X is as high as possible. Okay, so that the log of Q divided by P, is a big number. Okay, so yeah, any questions? I would say just focus on the left one because that's the one we're going to use in the. So let's not worry about the right one, but if you want to focus on the left one, then this is what is an example, just to give a more intuition. I don't know if it confused you guys or it's clear. You've not seen this metric before? Oh, in 575 or 572? Okay. Not maximum likelihood. Yeah, so maximizing the KL divergence is the same as basically maximizing likelihood. Yeah. So maximum likelihood, yeah, maximum likelihood is just this, right? So if you have some data, okay, some let's say two-dimensional data, then so ignore this is about specifically for Gaussian mixture models, but for anything, you would have just a likelihood, probability. Actually, this is not. This is like has a little bit more things going on, so let me not use this slide. Yeah, but maximum likelihood is just this. So if you have a bunch of data points, you want to fit a curve, then there's an appropriate. You just want to figure out, okay, let's say you're fitting a Gaussian among these points. Okay, it looks pretty bad to fit a Gaussian for these bunch of points, but if let's say you want to fit a Gaussian, then you write what's the probability. You write a one-dimensional Gaussian expression, and then say, hey, what's the mean and variance I should pick, so that the likelihood of all this data is as high as possible. Right? That's literally the. So what is the likelihood of the data for each point? You just write, under the current parameters, what's the probability mass being assigned to this point? Okay, so that's maximum likelihood. But let's come back to our slide. Yeah. So we are here, and what do we want to do? Just to not lose track. All we want to do is under this graphical model, which has Z and X, and we want to maximize likelihood of the data, which is our data is X's. We just don't want to deal with this integration. It's just too hard. And so we're going to try to do some tricks so that we can work with a slightly different objective. Okay, so that objective can be maximized, or the negative of that objective can be minimized. And it turns out that the negative, when we're trying to minimize the negative of that objective, it looks like exactly like the reconstruction error plus a loss on the Z space, and that loss involves the KL divergence term. Okay, so yeah, so this expression is not needed. So KL divergence term looks like this. Okay, so the first argument appears twice in the numerator as well as in the averaging. The second argument only appears once in the denominator. Okay, that's just if you want to remember what this version of the KL divergence is. So it's not symmetric. It's not a distance measure. Okay, so for example, if you think of a distance between 2 points, it's let's say in one dimension, it's a minus b the whole square, right? Let's say, or square root of that. The absolute value of a minus b, or if you have two vectors, right? If you remember, it's vector 1 minus vector 2, 2 norm. right? So that would be like a distance measure. So it's symmetric, whether you say vector 1 minus vector 2 or vector 2 minus vector 1 is the same value. Okay? Here it's not the case. If you flip P and Q, you're going to get something different because P appears in 2 locations, whereas Q appears once, right? It's not symmetric. Okay, so let's start with our likelihood objective. Okay, so it says VAE derivation, but basically all we're trying to do is get to the objective function. Okay, so again, I am repeating it for the nth time. For most of supervised learning, we didn't care about the objective function because we thought it was cross entropy loss, okay? And we didn't care anymore. Here now, with unsupervised learning, typically you want to think carefully about what is the objective function. And that's why we are talking about this. So here actually for VAE, it's a little bit natural because VAE at the end of it is a graphical model. And so most of the times you are thinking of maximizing the likelihood of your data. Okay. So P of Xi is what you care about maximizing, or log of P of Xi, which is the likelihood of the data, log likelihood of the data is what you want to maximize. Okay. But the problem is that likelihood of the data, X part, because of the way we set up the graphical model, involves integration and integrating out of Z. Okay, which is kind of hard to do. Okay. Because you don't want to do that integration, it turns out that we'll do some manipulation so that it looks like a reconstruction error plus a loss on the latent space, which is easy to, these are things that are easy to handle. So there's not going to be any integration. So we'll start with, so this is the likelihood of the data. And so we're going to take an expectation with respect to Z. Okay. First of all, so this likelihood of the data is a thing which depends on X. And if you're taking expectation with respect to Z, it has no effect. Okay, it's like saying expectation over Z of a constant. Okay, those two are not related. So we can always add an expectation, okay, because this term has nothing to do with Z, right? So this is pretty valid. So you can add that. Then what you can do is multiply and divide by the conditional probability of X given Z. Okay, so sorry, not the conditional probability of X given Z. So what you can do is this marginal probability. You can say that this probability is equal to the joint probability divided by the probability of Z given X. So that is easy to see, right? So P of X times P of Z given X is equal to P of Z times P of X given Z. That's just whether if you have a joint distribution between X and Z, you can write it as probability of Z times probability of X given Z, or you can write it as probability of X times probability of Z given X. Okay. So that's what we're doing. We're just replacing this single term with 3 terms, these 3 terms. Okay. That's just Bayes' rule, or just a definition of conditional probabilities. Once you do that, and you can already see that the moment we have numerators and denominators, we're going to try to massage it into some sort of a KL divergence. Okay, that's what we're going for. While doing that, we want to kind of get rid of somehow this integration issue. Okay, that's actually the key thing. I'll point that out. So after this, what we want to do is now start trying to see, okay, how do I pattern match so that I can get some sort of KL divergence type of expressions? And so for that, one trick is just multiply by constant, which is Q of Z given X divided by Q of Z given X. So same term, numerator and denominator, we just multiply. Okay. There's no nothing new happening. So we just added multiply and divide by the same quantity. Okay. Now you can see that starting point, we did not have anything to do with Z, but now we have started introducing Z's. Okay. And there's an expectation with respect to Z. Okay. So now what we're going to do is now carefully select some quantities so that we can have some KL divergence type of terms. Okay. That's what we're going to do. So here are 3 terms that we're going to split it into. First thing is we're going to take P of X given Z and then put it in the first term. So log of P of X given Z, we're going to extract it out, and that's my first term. Okay. This term will retain it. And then the second term, we're going to take Q of Z given X and P of Z. So this term divided by this term. And because we are inverting it, we're going to put a minus sign in front. Okay. So log of A divided by B is minus log of B divided by A, right? So we extracted this term and this term. And then finally, the remaining guys, P of Z given X and Q of Z given X, they are just captured here. Okay. So those are just by using just a definition of logarithms, we split it up into 3 terms. Okay. So this is just manipulation. So far, we've not gotten around the fact that we still have that integration. So remember so we know that this thing, at least cannot, if you just naively think about it, as an integration with respect to Z that we need to get rid of. so far, all these tricks have, they all are simple tricks. They're not going to change anything about the hardness of this integration thing that's present. Okay. Uh, in fact, where is the hardness present is going to become clear in a second. So let's actually now see that this term here is the KL divergence of Q with respect to P. Okay, that's just by definition. This is just expectation with respect to Z, where we chose Z to be defined with respect to this, okay, with this distribution. So it's just it's by definition. We're just calling it KL divergence between Q and P. And the second term we're calling it KL divergence between again Q and P, where the slight difference is P is Z given X. Okay? So this is just a replacement, just defining what this expectation are. Okay. Any questions here of any manipulation? This is just manipulation, so it's a lower level detail. So we're almost there, right? So all we did is one bunch of manipulations, but the integration complexity that was there, that is actually, that is actually, we can kind of work with it. Okay, how do we work with it? So it turns out we can actually give names to these terms that we created. The first two terms, okay, we're going to call it the variational lower bound. And the last term, we're going to drop. Okay? That's where the integration complexity is. So let's see why we can drop this. So if you look at this, so currently log likelihood is equal to something plus something else plus last term. KL divergence, as I said, is a measure of similarity. The lowest value is 0 when P is the same, numerator is the same as denominator. And the highest value is when P and Q are dissimilar. Okay, it takes a high value. So it's a positive number. So we can drop this term. And then if we drop the last term, the left-hand side is going to be greater than the right-hand side, right? So because the last term is a positive, potentially a positive thing, if I drop it, then the left-hand side is bigger than the right-hand side. Okay, so that's the first observation. The second observation is that this term actually has our complex B in there, which is this P of Z given X. We don't have P of Z given X. P of Z, so figuring out P of Z given X is as hard as saying what is P of X. Okay. So what I'm trying to say is that we know P of Z, which we assume to be Gaussian, so there's nothing to kind of worry about it. We also know P of X given Z because we have the decoder, and so that's also known. But P of Z given X is not known, in the sense that if you want to get this, you have to do that integration, or if you want to get this, you have to do that integration. Okay, so somehow from left-hand side, right-hand side, we haven't gotten rid of the integration. It's still there. It's in this term. And that term nicely appears in the last term, which is basically a positive quantity. So we can just drop it. And so, okay. So this is why it's called a variational there's a variational approximation going on. Okay. Why the word variational is because we were trying to originally maximize likelihood. Instead, we know that one of the terms is kind of hard. We couldn't still get rid of that hardness in the likelihood maximization problem. We dropped it. And so what we have left is a lower bound on the likelihood. Okay, what we have left is a lower bound on the likelihood, and we're gonna maximize that quantity instead. Okay, so this is called a variational approximation or a variational lower bound. Okay, variational just means like the optimization objective. It's just called optimization, the same as variation here, variational. So in fact, it has a name in the literature. It's called variational lower bound. Okay, or evidence lower bound is also sometimes used. So basically, what I'm trying to say is that dropping the last term gets rid of the integration challenge, and so now we are only left with something with two terms where things are easy to tackle. Okay, in fact, the first term turns out to be reconstruction error. Okay, so although in this expression it doesn't look like that, it's actually just a reconstruction error. Okay, and the second term is exactly some sort of a latent loss in the Z space. It's the difference between our preference, which is the Gaussian distribution, and the distribution being generated through the encoder. Okay, so the encoder given X's is generating some distribution on the latent space. And how far is the distribution from the our preferred distribution, which is the Gaussian distribution. That distance is being captured by the KL divergence. Okay. So the second term is basically the latent loss. So that's how you get the reconstruction error and the latent loss. So any questions here?
What is dropping our last term, which was the KL divergence of that has an effect on our.
That means we are approximately, we're not originally maximizing likelihood, we are trying to maximize the proxy quantity. So we are not maximizing the original thing, we're maximizing the proxy quantity because maximizing the original quantity is hard because of the integration. Okay.
That will have an effect on the accuracy of our model.
Yeah. So we don't compare that how much the gap is because we're not even able to tractably compute what if we did not do the approximation, how the results look like. We don't have a handle to it. Okay. So this is an example of a problem where maximizing likelihood is hard. Okay. Another problem that you might see in 575 if Gaussian mixture models are covered is the notion of is exactly the same problem. So you have a Gaussian mixture model, which is if you remember, it's just a mixture of Gaussians that you're putting it on clusters of data points, and you're just figuring out the means and variances and how much the mixture coefficients are. So that problem, if you want to just maximize the likelihood of the data under the Gaussian mixture model, it's going to be hard. But instead, there's a way to kind of introduce latent random variables, extra random variables, just like we introduce here. There's an extra z that we introduce. It's not part of the data. You can introduce latent random variables, and then you can solve a proxy for the original likelihood of the data. Okay, solving for the proxy objective because you introduce extra latent random variables in the Gaussian mixture models case is something that you would see maybe in 575 or 572. And so that problem is generally solved using what is called expectation maximization. Okay. The whole reason for expectation maximization existing is that you can't maximize the likelihood directly for Gaussian mixture models, which are the simplest. It's not even that complex, right? At least in describing what the model is. So what I'm trying to say is that maximum likelihood is the guiding principle, but in many cases you can't maximize the likelihood directly. And so in the Gaussian mixture models case, you maximize through a proxy, which is called expectation maximization algorithm, but it is maximizing something, but it's a proxy for the original objective. Similarly, for VAEs, instead of maximizing likelihood, we're maximizing a evidence lower bound, which is basically some reconstruction error plus some loss in the latent space. Okay, and similarly for latent additional allocation, which we talked about like 2 or 3 lectures ago, which is this topic modeling approach. I remember we're creating a distribution over words and some sort of topic distribution, additional distributions parameters that we are trying to learn. So even in that model, it's a graphical model. There's a topic distribution from which you're sampling word-specific topic values, and then given that you're sampling from the words. So even in that model, the maximum likelihood objective is hard to figure out what is the parameters of that model. So there is a way to kind of do variational approximation there as well. That's why I skipped over the training of that model, because that also involves some variational approximation. Okay, and in fact, it involves variational approximation and expectation maximization. It's like a double combo, so it's even harder to kind of discuss at the first go. So just commentary on this. So you should not be surprised that this is like a one-off esoteric way of doing something. This is pretty common with maximizing likelihood, that sometimes it's challenging, and so people look for ways to kind of proxy or some sort of lower bound or some approximation of the likelihood that they can maximize. Okay. Any other questions? Okay, so let's kind of summarize and take a break. So here's a full picture, right? So in terms of architecture, it's almost the same as autoencoder, except now you have these, 2 separate vectors that are the parameters of a normal distribution from which you're sampling Z. And then from Z, when you go through the decoder, you have now parameters of another Gaussian from which you're sampling X hat. Okay, so there's like a 2 sampling step that's happening. But otherwise, it exactly looks like a autoencoder architecture. Obviously, the objective function is now how far is X hat from X, and also how far is the distribution that the encoder is kind of creating given X's, how far is it from the distribution of z's, which is we are assumed to be unit Gaussian. Okay. So there's a second term which involves the KL divergence between the distribution of z and what is the distribution of z being induced through the encoder given the unknown distribution of x. Okay, that's the new objective function. And this is just an image of like how you would think how image that encode and decode networks look like. Exactly this part you should be able to see that this is just a convolution neural network going from a image to some sort of a tensor to a tensor to a tensor. Eventually you get a vector. Okay, from an image to a vector, it's kind of CNN. And the opposite side, the transpose convolution network is going from a vector to a tensor to a tensor to a bigger tensor. We saw that that was also just linear transformations, and so you'll reconstruct the image. Okay, so it is, it is fairly complex if you just think of it from scratch. But since we already have a CNN block that we have been very familiar with, and we just saw this block a little bit earlier in the autoencoder case, the complexity should only be focused around how can we sample that autoencoder was not able to do. How can we generate samples? And for that, we introduced the notion of random variables, talked about the joint distribution that led to the likelihood expression, which is hard. And so that led to the elbow evidence lower bound objective, which involves reconstruction plus latent loss. Okay. With that, let's actually, yeah. So it was introduced 10 years ago, actually, by these authors in a conference called International Conference for Learning Representations. So this is like early part of deep learning evolution 10 years ago. So this is a paper, and they have some nice results here. So before taking the break, I just wanted to show you this. What you're seeing here are generated images from MNIST, CIFAR10, which is what you used already. And there's also labeled faces in the wild data set. So this is actually generated images from that time. Okay, so this is 8 years ago. Looks pretty, not as good as like some of the modern generations, like diffusion models that you've seen or DALI models that you've seen. But this was the kind of just 8 years ago. So you can see how much progress we made over just 8 years. Leftmost figure is just talking about the generalization capability. So this is exactly what autoencode would not do. Where, for example, with MNIST data, if you embedded it into load, you did a VAE, you trained a VAE. Then, for example, if you look at once you train the VAE, then forget about the encoder. Let's look at the decoder, and then on the Z's, besides Z's are unit Gaussians, but you can always, instead of sampling, we're just showing if I vary Z1 and Z2, which are like the two coordinates of the Z vector. Think of Z as like 10 dimensions, and I'm focusing on the first two coordinates. Here I'm just saying as I change Z2, as I change Z1, how does the output change? You can always do that, right? So you can say as I perturb my input, as I vary my input, how is the output changing? In terms of generation, you can see that 6 is getting converted to 7, and then 7 like looking obviously getting converted to 1s and 2s and 3s and so on. Okay, so that's how it's generalizable. Whereas if you did the same type of exercise with an autoencoder, you will not see these types of patterns. You just, autoencoder is just trying to compress data. You're not, at least in theory, you should not be able to generate new data points. Okay, any questions here, or we take a break? Okay, we take a break for 10 minutes and resume at 7:45. Okay, so the next model we're going to look at is GANs. Actually, let me quickly show another thing. So this is a project. I mean, although I'm showing research projects, don't worry about you don't have to go up to this research level, but there's some good ideas that are kind of building on some basic building blocks. And so this project I just wanted to show because it's a collaboration with folks in the West Campus. And what we do is actually work on a variational autoencoder, right? So it's basically building on a VAE that we just saw earlier. And on top of that, it's called a graph variational encoder. So we're working with graphs. Okay. By the way, graphs are just if you think of a graph representing a graph, how do you represent a graph? You mostly think of an adjacency matrix, right? So for every node, you can put an entry value 1 if the the two nodes are connected, and if not, you leave a value 0, for example. So graphs can be just represented as matrices. And the moment you have matrices, you can think of it's matrices. It's a matrix, so it's like an image, right? So think of image-based ways that we've been talking about. You can actually just work with graphs also. So you can do you can compress a graph into lower dimension, and you can bring the graph back into upper dimension, higher dimension, and you can say, oh, how much did the autoencoding process work? Like also you can do the VAE version of it. So this, just a brief comment on this project, if there's a picture. Yeah. Just so you just zoom in as much as possible. So this, so what is happening here, right? So it's a context where what we want to do is so what we want to do is kind of work with two different matrices, two different sources of data. Okay, what are those two different sources of data? One is called the structural connectome, and the other is called the functional connectome. Okay, so what are these? These are can think of these inputs as some sort of the lower matrix is capturing activity in different parts of the brain. So through MRI readings, just looking at co-occurrence of different regions of the brain triggering. Okay, so that's one input, and the second signal is just the kind of connectivity of the brain itself. Okay, just how the brain is structured. Okay, so this is brain-related data. One is related to brain activity, some sort of temporal data, which is compressed into some sort of a matrix here. And then there is a structural connection of, okay, region 1 is connected to region 2, region 3 is connected to region 4. It's just a region connectivity. Okay, so so those two are the inputs. And from those, what we want to do is actually just classify how does this data differ from healthy controls or healthy subjects to subjects who have Alzheimer's. Okay, so how does the brain patterns kind of differ between two populations? And for that, one of the steps we do is going from these matrices to a low dimensional space. Okay, and how do we do it? Exactly the Q and P's that we're talking about. So we go from a user encoder, go to kind of compress both these matrices into low dimensional space, and then do some sampling, and then decode, and then reconstruct at least one of them. So in this at least image, you can see that we're only reconstructing one of them because of various reasons. And so the objective function is to reconstruct really well this matrix and then have the KL divergence loss that we're talking about in the latent space. Okay. Once we do that, then we are actually further encoding all our data set into this latent space, and then doing a further compression to get some further second level of compression. Okay? So we're doing two levels of compression. One level of compression is generalizable, so you can actually reconstruct new brain matrices. Okay. In the second level, we just care about like minimizing the dimension, like some sort of projection into low dimension. And then we relate it to the two classes, as in we can see whether these vectors and the labels are whether this person is healthy or whether they have Alzheimer's, whether we're able to kind of just do some sort of a binary classification. Okay, so I don't know if the result is here, but just wanted to show that whatever we're seeing in the class is such a recent thing, right? Not just VAEs, but sure, CNNs are a little bit old, LSTMs are a little bit old, but transformers, VAEs, GANs that we'll see now, they're all in the past decade, okay? And much less than a decade for sure. So there's a lot of activity on both in the classroom, like us doing toy problems, canonical problems, but also a lot of activity in the and people trying to use that for various use cases, which is what I've been showing in this class. But also people developing the architectures also, they're searching for better and better architectures, training bigger and bigger models on clusters of GPUs, and dealing with not just model training and model splitting and all that, but also GPUs failing, right? The moment you have 100 different hardware units kind of trying to coordinate and do something, things can fail. Okay, that's very common in the computing systems. Anyway, just wanted to give you a sense of that what we're studying in the class is pretty recent. Okay, so let's with that final comment on VAEs, let's talk about the next model, which is GANs. Yeah, and we already saw a picture, to motivate GANs, which is this person does not exist.com. I'm not going to show it again, but that was an example motivation. But GANs have like so many. I think I have I don't know if I opened that site. Oh yeah, so you can look at some other. So here's a repository that I just picked right before the class, which is called GANs Awesome Applications. And if you look at the list of applications here, font generation, interactive image generation, text to image, image editing, face aging, 100 different applications here. So you can see that there's so many things that people have worked on with just the same canonical idea that we're going to look at next. Okay. Okay, so what is the problem scope, right? So the problem scope is still the same as before, which I stated last time, which is we want a sample. Okay, given a bunch of training data points, we don't care about dimension reduction. We don't care about many of the other unsupervised learning problems. We want to compress that data or kind of convert that data into a black box. And from that black box, we want to generate new data points. Okay, they look as good as those original data points, and they're not exactly the same. Okay? They don't just look up. Okay? And so in particular, we were working with images. So that's the objective, to sample new images. Okay? And one of the example models that we saw is VAEs. And GANs also want to achieve the same thing. And we're going to see how they achieve it by, again, discussing the architecture and discussing the objective function. Okay? So the combo is important here. So instead of working with an explicit density function, which is what we did with VAEs, there is a graphical model, there's a random variable involved. There's not going to be any random variables, no such thing here. But still, we are able to create a black box from which we can sample new images. Okay. So so it's a name itself. There's an A. It stands for adversarial. So it takes an adversarial approach to defining the objective function, okay, or the loss function. And the adversarial comes from game theoretic. I guess game theory is a subfield of econ or applied math, basically. And so adversary just means the opponent. Okay? So there's going to be two learners, okay, two neural networks that we're trying to learn their parameters. And it turns out that when we're trying to learn their parameters and we do gradient descent, their objective functions are in some sense opposite of each other. Okay? In the sense that if one is maximizing some function of parameters, then the other one is like minimizing the function of parameters, okay? Something like that. Okay. So and both of them are learning, in the sense both networks we're training in each iteration of one gradient descent followed by another gradient ascent, for example, and then a gradient descent, and so on. Okay. So that's the adversarial aspect. So there's going to be two networks. So firstly, so I'm going to explain this in three views. Okay. So if you don't catch in this view, we'll see the same idea again a couple of times. So there's going to be two functions. Okay. Two functions or two players or two networks. One, we're going to call it as D of X. The other one, we're going to call it as G of X. Okay. D actually stands for discriminator. G stands for generator. So there are two functions, okay, or two players. So what does the player D want to do is that that player or neural network, if it gets input from real data. So remember, we have a bunch of real images from which we want to get this black box from which we want to sample. So we do have these images. This player, this network D, if I get a sample from my actual, my set of real images, then it has to produce a number close to 1. Okay, so that's its role. So that's what it's. So whatever learning it's trying to do is to just learn that, okay, hey, it's an image from my training data. I want to produce a number close to 1. But if it's not from training data, I want to do the opposite, which is produce a number close to 0. Okay. what is the input which is not from training data, which that input is going to be something that's generated by the generator, okay, and it's a synthetic output. Okay, so anything that's not that's not part of the training data, I want to produce the output 0. That's what the d of x does. So for real data, this is one scenario. For the non-real data, what does the G network do? It takes an input as a noise, very similar to the VAEs noise, right? We start with the random Gaussian. So we start with noise, and we have this G that produces something. Okay, that something hopefully is, a good image. Okay, but it produces something, and that something, when D sees it, it has to produce a number close to 0. Okay, so D of G of Z, D tries to make it close to 0. Okay, so we choose the parameters of D such that it's close to 0. By the same time, G is trying to produce outputs such that when it is passed through D can produce close to 1. Okay, so G still has control, right? G can produce better and better quality outputs such that it can confuse D such that D is now starting producing 1 instead. Okay, so that's the goal for G. G has to confuse D to kind of make it start producing ones instead of close to zeros, produce numbers close to 1. Okay, so that's why this adversarial. Okay, because on this type of data, D definitely wants to go produce 0, but G wants to make D produce 1. Okay, so they're against each other. Okay, so that's the one way to kind of explain it. If it's not 100% clear, we'll come back to that kind of figure again. So let's say G is producing G is producing, given Z is producing, Z is just noise. Okay, so some sort of source of noise, because at the moment we have to sample new things, there has to be some source of noise. Otherwise, it's unclear how to generate different answers every time. So given some source of noise, G has some parameter and it's producing some value X. Okay, and given X, D is producing a value between 0 to 1. Okay, it's not curly braces, it's like an interval. Okay, so that's what we're doing. So going from Z to X's, from X's, discriminator is trying to produce a number, at least for these X's, that's produced by G. Discriminator is trying to produce a number which is close to 0. Okay, now what's happening in this figure is there are a lot of overlapping things. So firstly, let's say G is producing this G is producing the curve which is the green curve. G is producing the green curve. And let's say the data, the training data that we have is the black dots. Okay, let's say the black dots, they're in this illustration they look like a Gaussian. Let's say the black dots are shifted to the left and the green curve is shifted to the right. Okay? In that case, D can do a really good job. D knows that things which are to the left of some threshold, there are black dots. So they should be, I should produce 1. And if the input is kind of right of the threshold, that I know the green curve is, in that region, I should produce a 0. So D, which is shown through this blue dashed line, you can think of it like a step function. Okay, so anything to the left of the threshold, because it's black dots, it'll be 1, and anything to the right of the threshold, since it's green curve, it'll be 0. Now, G's objective is to make the green curve closer and closer to the black dots. Okay, closer and closer to the black dots. That way, the discriminator is not able to kind of figure out what is the decision boundary between, if left side versus right side, which one is what, we don't know. In the ideal case, if the green curve exactly overlaps with the black curve, then the discriminator is like, I don't know what is real and what is not real. Okay, and so that's what's going on. That's what we want to achieve. Okay. Any questions here? So far, it's all been like we're talking about, okay, some mechanics of two players trying to kind of go against each other and so on. We'll see what the explicit networks look like and what the objective function looks like. Okay, but the objective function is exactly inspired by sort of a, they look like cross entropy losses actually, but you'll see that since there are two networks, their objectives will be kind of contrasting each other. Okay, so again, just at a high level, the generator network is trying to fool the discriminator by generating real looking images. And discriminator is trying to distinguish between real and non-real images. That's what we're trying to do. So that's what the discriminator network is doing. So things generated by the generator network, I want to make output 0 or not real, and things which are in my data set, I want to say they are real. Okay? So discriminator, you can just think of it as like a CNN actually, because it's taking image as an input and producing a binary label. So it's exactly what ANTs versus B's code was doing. So you can just kind of pick that part the same. The generator network, it's going from a vector to a image. So it is basically doing exactly the transpose convolutional network that we saw for VAEs and autoencoders in last lecture. It's exactly the same. Okay. Okay. So this is again same picture, kind of shown for the third time, but basically this discriminator and generator have parameters. There are different parameters, and discriminator it's a binary classifier, right? So it's just a 2-class classifier. So you can imagine it will just have a cross entropy loss. But the loss is kind of, you can split the loss into loss based on this data and loss based on this generated data. Okay. And note that there is no, unlike a VAE, there is no, so if I give X to the discriminator and discriminator says it's actually real, the generator is not trying to create some sort of a reconstruction of X. Okay, there's no correspondence between the training data X's and the generated data. Okay, so there's no X hat, very similar to what we had in VAEs. In VAEs, we were given X as the training data. We were actually trying to reconstruct X itself during training. Here, the generator's job is just generate generate realistic looking images, not corresponding exactly when I give an image of let's say if I'm CFAR10, if I give an image of an airplane, it's not like the generator is trying to create an image of an airplane. There's no synchronicity or like any coordination like that. Okay? Any questions?
The loss will be inverse for discriminator than for generator, right?
Yeah, we'll see the loss in the next slide. So I want to just talk about here. I just want to highlight it's exactly the same picture where we want to wants to discriminate between this side and this side. Except all I wanted to point out was that when discriminator discriminates, for example, in this picture, it's a little bit confusing. That some people could interpret that G of Z is supposed to be some sort of approximation of X. It's not, because G of Z is some generated image, X is some real image, and then discriminator is just, they're not related, they're not same airplanes, or they're not the same thing. It's just the question is between real and fake. It's not the question about real and fake of the same image. Okay? It's not. So let's look at the object function. Okay. So what we are actually doing, I mean, you will see that another interpretation to give to this is it's called a minimax game, but let's not worry about the extra terminology, minimax game, and so on. So what is the loss of the discriminator? Okay, the loss of the discriminator, we can think of the discriminator has a loss for the training data part and a loss for the synthetic data part, right? Let's say the discriminator sees 100 examples. Some examples will be from the training data, some examples will be from the generator, right? So I'm just trying to say, okay, if the examples from the training data, let me define the loss. Examples from the generated data, let me define the loss. Okay, because we, when we are designing it, we know what is real, what is fake, and discriminator has to kind of be correct on the true labels that we know, right? So on the real data, this is the loss we want to kind of write down. Okay? So what is the loss? It's the expectation over the real data of log of the discrimination, log of d of x. Okay. So what does it mean? If the discriminator produces a number close to 1, then this log of something close to 1 is like a very small number, and so negative of very small number is very small. Okay? So all I'm saying is for the real data, if you produce a number close to 1, loss is low. For the real data, if you produce a number which is far away from 1, like close to 0, then this loss is really high. Okay? So that's just exactly the same intuition that you can have for cross entropy also. Like the less probability mass on the true label, then the bigger loss you have on that example. Okay? The true label here is supposed to be 1. That's why, if more probability mass on the true label, then your loss is low. Okay? Now let's focus on the second term, which is loss for all the non-training data points. Okay, on non-training data points, I need to produce, discriminator has to produce a number close to 0. Okay, so yeah. Okay, so if the discriminator is producing a number, okay, some number, okay, let's say it's producing a number close to 0, then 1 minus that number, if it's close to 0, then it's close to 1. So log of that number is going to be very small. And so the loss, if the discriminator produces a number close to 0, is going to be small. Okay, so for these data points, if it does the right thing, which is produce a number close to 0 instead of 1, then the second term is going to be small, right? So for a data point from training data, produce a number close to 1, your loss is small. For data points which are not from the training data, if you produce a number close to 0, again, loss is small. So to minimize the loss of discriminator, you have to kind of discriminate between real and non-real images. Okay. And then what we do is second part, we'll just say the loss for the generator is just a negative of the discriminator. Okay. This is why it's called a minimax game, in the sense that the gains for one player are exactly the opposite of the are the losses for the other player, in the sense that the sum is a constant. So sum of these two, JD plus JG, is just 0, right? If one player wins $1, the other player loses $1. Okay? That's why it's called a minimax game, okay, or a zero-sum game. Okay. In fact, you'll see that it turns out for the loss for the generator, it turns out that only this term counts, because the first term is just a function of the training data, and the generator parameters have nothing to do with the training data. So you will see that the second expression is actually simpler. Okay, but we'll see. Actually, this expression I'll show again in a slide with a little bit more symbols. But before that, what is the optimal strategy, right? So we already kind of saw this here, right? So what is the optimal strategy? Optimal strategy is for discriminator to kind of mimic more and more the training data, so that it kind of completely overlaps with the training data. In that case, discriminator is like unable to know what are the black dots versus what's the samples from the green distribution. And so the optimal strategy for the generator is to create, make P of G theta to be as good as P of D. And the optimal strategy for the discriminator is to flip a coin. Okay, there's nothing more to do. So yeah, so the optimal strategy for the discriminator, if you don't make it exactly the same between the data and the model is the generator that's producing, then the discriminator's optimal strategy is to do probability of data divided by probability of data plus probability of model. So if all I'm saying is probability of model is the same as probability of data, it's 1/2. P of D divided by 2 times P of D is just 1/2, right? And the optimal strategy for the generator is to find parameters such that P of D is actually close to P of M. So obviously, if P of D is equal to P of M, then it's 1/2, right? So that's all I'm, in the illustration example, we just saw it. So instead of like something going like this, it'll be flat at 1/2, because you're not able to distinguish between the black dots and the green curve. Okay, so given that, let's look at, we have kind of covered the objective function, and we have covered the what is the game aspect here. So next, let's just briefly do a quick discussion of the training process. So the way you train is you create a mini batch of your real data, like a bunch of, let's say 10 images. You generate 10 images from your current generator. Okay. Now these 10 images and these 10 images have nothing to do with each other, in the sense that there's no correspondence. Okay, that's what I was trying to point out. And VAEs, there's some correspondence between reconstructed and so on, but here there's a bunch of 2 sets of images. They're not related to each other. Then given these 2 batches, you can score the discriminator, as in like do the forward pass of the discriminator and see that the loss function, because loss is a function of both the real data and the generated data. So you can see what the loss is. And then backprop through the discriminator, update the parameters such that the loss is, kind of, so that you're kind of in the right direction of the, you're updating the parameters such that you're hopefully, have lesser losses next time. Okay. And then you can score the generator as well. So you can say, okay, given the current generated images, when it passes through the discriminator and you produce a bunch of numbers, how much did the generator, what was the loss for the generator? Remember, loss for the generator is just minus of the whatever the loss for the discriminator is. And then you update the parameters of the generator so that that loss is minimized. Whatever the current loss is kind of further reduced. Okay, it's just a grain update you do. So here's a recap of exactly what we discussed with full set of symbols. The minimax objective has parameters, generator parameters, and discriminator parameters. Now, the first term corresponds to the true data. Okay, true data is only kind of interacting with the discriminator. So true data, remember, we were trying to our loss term involved log of the discriminator, right? This is the same as the expression from before. And then for the synthetic data, now we have a log of 1 minus discriminator, but the discriminator's input is now the generator's output. Okay, I'm explicitly calling this out. Okay, this is exactly the same expression here. This term, except we drop the minus sign because whether you are minimizing minimizing this loss or maximizing the likelihood, it's the same thing. Okay. So here in this expression, we're maximizing over discriminator. That's why I dropped the negative sign. We could have put the negative sign and then said min over d, theta d, and max over theta g. Okay. So the reason why we're calling it a minimax objective is because there's a min over one set of parameters and the maximum over another set of parameters. Okay. So given this is the objective. You can just do a gradient ascent on the discriminator because I dropped the negative sign. We are maximizing on the discriminator. So gradient ascent. So it's exactly the same expression, but we're maximizing over theta d. And then we want to minimize our theta g. So it's exactly the same expression, except you will see that one term is missing, which is this term or this term, because that doesn't depend on z. Okay, so that's why it's looks like only one term, something different from before, but it's not. It's just one term because this first term doesn't depend on z. Okay, so discriminator network and generator network are two players. One is doing a gradient descent. The other one is doing a gradient descent. Okay. That's why they are kind of opposing each other of the same, almost the same objective. Okay, so with that, as the discriminator, like for example, here for real images, the discriminator picks a loss and updates the discriminator weights. Maybe at the beginning, when discriminator is getting updated, generator is like, we're not touching the weights of the generator. Generator produces some bunch of images. Discriminator produces a bunch of images. Sorry, we have a bunch of images from training data, and given these two, we updated the parameters of the discriminator. Then we seal the discriminator, and then whatever we generated, we look at what number that is, and then update the generator weights to kind of improve our generator score. Okay, so it's just tandem. This is exactly what we are doing here. So we want to update the parameters. Remember, we can just do forward pass and find the gradient with the loss with respect to the parameters and just update our parameters. Same thing with this generator as well. We can do the forward pass, find the loss, and take the gradient of the loss with respect to the parameters and update the parameters. Right? One is the ascent, one is a descent. That's the only difference, and that's being pictorially shown here. When we're doing the update of the parameters of the discriminator, these parameters are fixed. When we're doing the update of the parameters of the generator, discriminator parameters are fixed. Okay, that's all. Okay, so and then we have seen this before. I just wanted to show that there's a GAN with literally the name DCON GAN, DC GAN from 2016, which does exactly that reverse operation that we've been talking about since autoencoder from last lecture. It's going from a vector to a tensor to a bigger tensor to a bigger tensor, bigger in height and width, reduction in the depth to finally an image. Okay. So with that, let's kind of just wrap up by looking at a few examples. We already saw this person does not exist, but that's more involved with some extra bells and whistles. So here's the DC GAN model that's kind of showing the same type of activity that we did with the Z1, Z2 that we were doing for MNIST. Okay, so here we're showing in the latent space, the input to the generator. We're saying, okay, let's pick two coordinates like this, like a 6th and 10th rows. Sorry, 6th and 10th rows. Okay, so yeah, these 610 rows correspond to these rows here. What I'm saying is very similar to the VAE, where we picked latent space and we said, okay, there are Z1, Z2, and we slightly vary them. How does the generated images vary? Here we're doing the same thing. As the latent space, we're going from one point to another in the latent space. We are kind of varying the output generated image like this. Okay, so obviously these images are not high resolution because they're from 8 years ago, actually 9 years ago. But you can see what the principle is, right? So you can see going from like a bed to a slightly different bed, or something in the window without a window, and so on. So you are interpolating and generating new images that were not there in your training data. Okay, and obviously these images may not, for a visual naked, you can actually see the flaws very easily. Okay, and much of the effort in these types of models is to kind of get rid of these flaws by training more, using a bigger network architecture, and so on. It's the same principle of training. It's just bigger and better networks. Okay. You can also do some sort of arithmetic. We saw this type of thing with word2vec. So here you can, it requires some extra effort, but basically what they're doing is going from a vector that generated a man with glasses and a vector that generated a man and a vector that generated women. If they kind of add them up, okay, so subtract and then add those vectors, and then that's a new vector with which they do a forward pass on the generator. They're able to generate these types of images. Okay. Just to kind of show how the interpolation works. So there's a nice way to go from the latent space is actually capturing addition and deletion of features appropriately. Okay. Now, how do you actually instrument this? You can do exactly what we're doing with VAE. You start with the Gaussian distribution over the latent space, sample a random vector, pass it through the GAN, pass it through the generator, you get a new image. Okay. That's there is some issues with these changes in objective functions. At least VAE's objective function was kind of the same in the sense of reconstruction error is like a square loss. So it's not too different from other losses that you've seen. So VAE doesn't have this issue, but GANs have an issue which is called mode collapse, which is because of this training process, which involves an ascent and a descent, right? So it's although if you look at the objective function, it's still cross-entropy type expressions, but there is a constant back and forth, of updating parameters because there are two networks being trained kind of against each other's objectives. And so mode collapse just means that, for example, if there was a distribution like this, okay, from top view, so it's a two-dimensional plot where let's say there's a bunch of peaks, as in bunch of Gaussian distributions, then it may turn out that if you try to train a GAN to learn, so let's say this is the distribution, real data distribution, and your GAN is trying to slowly learn that, okay, the data distribution should be like this. So you can see that the data distribution is not learning. So in this case, ideally what you want to go from step 0 to eventually is to get a pattern like this in terms of the GANs distribution. But you're not getting it because there's what is called a mode collapse. In the sense that it's focusing on one location at a time. So you're basically jumping around from, okay, oh, let's focus on this part, then jump to this part, then maybe jump to this part, and so on. So it's not getting diffused. It's not making any multimodal distribution. Okay, there's some fix to that. You can see somebody has kind of fixed, and eventually you can get to an appropriate distribution, which looks like the target distribution. But all I'm trying to say is that training GANs is hard because of this. One of the issues that people have kind of explicitly mentioned is called mode collapse issue. Okay, so the moment you're introducing more exotic training objectives, in fact, it's going to be harder to train. Okay, and in fact, even without exotic objectives, the moment you have depth, if you don't choose the right ReLUs, right nonlinearities, if you don't do the right weight initialization, if you don't do the batch normalization and things like that, then it gets very messy to train. And that's why all these innovations about skip networks, skip connections, and layer normalization and batch normalization and variations are there, and dropout and all that, right? Yeah, so here I think it's going from left to right. It's just showing an improvement in generated images as a function of training. Okay. Any questions here?
About the discriminator model.
Yeah.
So doesn't the GAN primarily depend on the quality of the discriminator model, right? Since if it doesn't capture the
Yeah.
distribution of the real images, it might be arbitrarily discriminating the real and the generated images, right?
Yeah.
And once we get the test data, which is out of the distribution, it will collapse.
Out of distribution aspect is something we can discuss in a second. So, um, so you're saying the quality of the discriminator influences how well we learn, how well the generator is able to learn to generate good images. Yeah, that's true, right? So you have to kind of visualize, right? So if you think of a regular neural network, all the supervised learning stuff that we're doing, there's a network, we give an input, and then immediately you get score, right? Whether it's good output or not, right? In supervised learning. In GANs, in VAEs also, somehow the the VAEs also, there is a decoder is producing an image, and then that image is being compared with the reference image, and then some sort of reconstruction loss is telling you how bad the decoder is, which is the generator, which generates images. Here, the feedback to the generator of how good it is doing is actually through the discriminator, right? So there is the real data, but this guy never sees the real data, right? So the generator is not even seeing the real data. The only way it knows how well it's doing is the real data influences the discriminator parameters, uh, and then the discriminator parameters are influencing what the score the generator gets. So it's really indirect. Okay, so yeah, your comment about discriminator quality and discriminator network model influencing generator output is correct. Yeah.
Also, what if the generator, the sample that is generating, is not really close to the real world image, right?
What if the generator is putting things which are not real world? Yeah, that can happen, right? That'll happen by default. The whole challenge of training this is to ensure that we get good representative images which kind of look like real world images but are not from the sample. Yeah. How do you get away? So by default, all I'm saying is that the default situation, if you don't make concerted effort in training, you will get garbage images and things which don't look real. Okay? There's a lot of effort to train them really well so that they look real worldish. Right. For example, I don't know if this one, I don't know if you can identify errors. Let's just refresh and see. I think all these look pretty good, but I mean, I don't know if you can see like some errors, right? So sometimes the ear is not correct. Sometimes, hair is not consistent. Yeah, there's a lot of issues that can happen. But yeah, this work is by some folks at NVIDIA, so they must have put in like a lot of work to get this running really well. So for example, I think this part doesn't look like it's well formed. Yeah, I mean, this is like maybe, so these are, I don't think this is being generated in real time. It's just flashing pre-produced images. But maybe in Hugging Face Hub, when you kind of use the inference and just see these type of models, you'll get a sense of how bad they are. Okay? Cherry picking is one thing, but you can see a lot of defects. Okay, so it's going to happen. Okay, you will see things which are not like realistic images, especially if you try to train a GAN. Okay, let's actually wrap it up. So VAEs, just to wrap up what we covered today, VAEs are like R generative models that use regularized log likelihood, basically. You can think of it as regularized log likelihood because there's a reconstruction term, but some sort of a regularization term, the latent loss term. They tend to achieve higher likelihoods in data, but the samples look blurry. Okay, that's what's observed. That's an empirical point. You can compare generated images with original images. This is what I was saying, right? There's reconstruction, so you can always compare with the training data. Whereas GANs, there is no relation to the generated images and the training data set. Okay. It's part of graphical models subfield of machine learning. So there's a principal theory in like explicitly defining likelihood and working around joint distributions and things like that. Whereas GANs don't have it. They basically use that supervised classifier, which is the discriminator, to get a sense of how good the generator is generating images. So clearly the discriminator quality influences things. There is no explicit constraint that the bed should look like a bed, right? So there is no reconstruction error or something like that. There's a game, although we said in equilibrium, the game is that the generator's probability distribution is the same as the data distribution, and the discriminator is like producing one half, as in flipping a coin. But in reality, because of the neural networks, it's actually an intractable game in the sense that there is no way to kind of get, just because we're doing gradient descent on both sides, doesn't mean we get to the optimum, which is discriminator is completely fooled and the generator is producing exactly the same as the discriminator's distribution. It's not guaranteed at all. Okay, so that's actually a, it's very easy to show this type of a claim. GANs do produce sharper images. And you saw stable diffusion also produces really good sharp images. Sorry, just diffusion models produce sharp images. Yeah, and you start with latent variables which are random, and then you deterministically transform it to an image. Okay, whereas in VAE, you start with a random sample, you get to a mean and variance distribution, from which again you do an extra sample. Okay, so there is like a little bit more sampling involved. Yeah, let's not worry about the other points. There are many variations. This is actually from some time ago. I didn't update the slides. There are like probably 2,000 or 5,000 plus GAN variations today by a lot of authors. And you saw that page, right? Awesome GAN page has a lot of use cases that is listed. So you can look at Google Scholar to see how many GAN related papers there are. There are lots there. Yeah, just in terms of pictures, this is what's happening. Encoder is encoding an image, and then decoder is decoding that image, but with a sampling step in between so that it generalizes. There's a reconstruction error. And because these are random variables, we are imposing that the Z is a Gaussian random variable. Okay. And so given an X, it's easy to find Z. So you can actually just go back. Given an X, you can find a Z. You have probability distributions, and generally you get blurry images. Empirically, that's been observed. GANs, you start with a random source, which is the Z, pass to the generator. A generator should produce images which are as good as the training data that the discriminator sees. So it's a little bit of an indirect feedback to the generator, say how good the images they are producing. And so there's no correspondence, there's no reconstruction type of a thing. Training data could be completely different from the generated images in terms of concepts. But that's what we're doing. Very sharp images are typically obtained. There's no way to go from an image to figure out what is this Z that led to that image. In a sense, you need to kind of do something more computation. Like you can always, given an image, you can figure out what is the Z that led to that image is a optimization problem. And there's no explicit probability density function. There's no P of X that you are kind of handling. It is a black box from which you can generate samples, but it is an implicit notion of what are samples here. Okay. Any questions with these pictures? Okay, if not, let's end here. VAEs are from 2013, GANs are from 2014, so kind of recent. Although there are some variations from decades ago, but very recent, 10, 11 years ago. A lot of applications. I mean, here I just listed like few of them, but if you look up on the internet, there are like lots of applications. And just to kind of wrap up, diffusion models that I briefly just teased with the new paper that was released with the text thing. They also fall in the same category. So yeah, this is a different class of models, diffusion models, very similar to going from an image to noise to image, but some slightly different ideas there. But they also fall in the same category of going from generating new images, which are not in any training data. So if you have time, I would suggest playing around with Midjourney or Stable Diffusion or DALL-E just to get a feel for like what is the quality of these models today. Okay, they are really, really good. And I don't know how many of you have seen OpenAI's Sora demo. Sora is a video generation, text to video generation, right? So it's all the same, same diffusion model based. In fact, diffusion model based and diffusion model is also based on transformers, the same transformer that we saw a couple of lectures ago. Okay, let's break today.